Hello. Today we're going to be talking about shrinks or stretches of parent functions. And when you were in geometry class, shrinks or stretches were also called dilations. So first of all, there's two different kinds of shrinks and stretches. The first kind is a vertical shrink or stretch. Remember, vertical is up and down. So what we're going to do is we're going to make something taller or shorter. So if you wanted to talk about this shrunk or stretched function, we'll call it h of x. And what you're going to do is you're going to take some constant c and multiply it by the parent function f of x. So c is a constant. Now it is a stretch. This function will be stretched out if c, or the absolute value of c anyways, is greater than 1. And like I said, this makes a taller graph because it's been stretched. Stretch means taller. It is a shrink if the absolute value of c is less than 1, like a half, and that's going to be shorter. So let's take an example of a vertical stretch. Let's stretch an absolute value vertically by a factor of 3. So that h of x function is equal to 3 times that f of x value, that parent function absolute value of x. So we know that's a vertical stretch because the 3 is on the outside of the function. So what this is going to mean is we are going to multiply the y's by 3 from the parent function. That's what a stretch means. We're going to change the y's one way or the other. So let's start with our table of values for the parent function. Absolute value -3, -2, -1, 0, 1, 2, and 3. Absolute value 3, 2, 1, 0, 1, 2, 3. So that's the start. That's the parent function. That is the absolute value of x. And then what we're going to do is we're going to multiply the y's by 3. So we'll say we'll do 3y. We'll set up a new table of values. The x's stay the same, and the y's get multiplied by 3. So we've got 9, 6, 3, 0, 3, 6, 9. And now let's take our straight edge and make a nice tall absolute value graph. Does not go underneath the x-axis. So we've got -1, -2, -3, 1, 2, and 3 on our x-axis, and we're going to go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So -3 to 3, -3, 9 is our first point, -2, 6, -1, 3, 0, 0, 1, 3, 2, 6, and 3, 9. And then since this is a V-shaped graph, we'll just use our straight edge to connect those points. A nice straight line. And here is our absolute value. And you can see that this is a taller graph than the original parent function. Let's have another example. Let's shrink a cubic by half the size. So we'll shrink a cubic by 1/2 the size. So we'll make it shorter by a half. So that h of x function is equal to 1/2 of the cubic function x cubed. And so this means we're going to multiply all the y's by 1/2. Or in other words, divide by 2. So let's set up our xy table, and remember we start with -2. And our parent function is 8, -8, -1, 0, 1, and 8. This is x cubed, or f of x equals x cubed. So what we're going to do now is we're going to do 1/2 of y. So take all those y values and divide by 2. The x's stay the same. And -8 over 2, -1 over 2, 0 over 2, 1 over 2, and 8 over 2 is 4. So now the y's go down to -4 and up to -4. So when you graph this, you can see that it's going to be a shorter function than the original cubic. So -2 to +2, 1, 2, 3, 4, 1, 2, 3, 4. So we have negative 2, negative 4, negative 1 1/2, 0, 0, 1 1/2, and 2, 4. So now we'll connect this with a nice S-shaped curve, and you can see that this is a shorter curve than the parent function. We've shrunk it down. The next thing we're going to talk about is a horizontal shrink and stretch. So that's the second type of tonight. 2, horizontal shrink or stretch. And to look at that function, the h of x value is going to be equal to f of, now inside the parentheses, inside the function is going to be that constant c times the x instead of the c being out here, it's inside parentheses. And whenever you do things to x's, whenever you manipulate the x's, it's the opposite of what makes sense, or what this is saying. What we're going to do is we're going to divide all the x's by c instead of multiplying them. And this is going to be a shrink if the absolute value of c is greater than 1, the opposite of what the vertical one was, and it's going to be a stretch if the absolute value of c is less than 1. So this would make a thinner graph. Remember, horizontal is going left to right. So if you're shrinking something horizontally, you're making it thinner. If you're stretching something horizontally, you're making it wider. So we either have a thinner or a wider graph. So let's have a couple of examples. Let's stretch a quadratic. To twice its size. So if you think about a regular parabola, if you stretch it to twice its size horizontally, I should say, what you're going to do is you're going to see h of x is equal to, if it's twice its size, you're going to have inside parentheses 1/2 x squared. You can't forget this parent. This is the parent function, and if it's twice the size, you're going to be dividing by a half, which is multiplying by 2. So what this is going to do is we are going to divide the x's by a half. And remember, dividing by a fraction is like multiplying by the reciprocal. So this is the same thing as multiplying by 2. All of the x's. Dividing by a half is the same as multiplying by 2. All right, so let's set up our xy table. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. And if you square it, now what we're going to do is we're going to say 2x, because we are dividing by a half, multiplying x's by 2. So we're taking all those x values and doubling them. So negative 6, negative 4, negative 2, 0, 2, 4, and 6, and the y's stay the same. So there are our table of values that we're going to graph, and let's see, all the y's are going to be positive, so we don't need to go above or below the x-axis, and we're going to go back to negative 6, 1, 2, 3, 4, 5, 6. Here's negative 6 to 1, 2, 3, 4, 5, 6 to positive 6, and up to 1, 2, 3, 4, 5, 6, 7, 8, 9. So negative 6, 9 is going to be about here. Negative 4, 4 is going to be up here. Negative 2, 1, 0, 0, 2, 1, 4, 4, and 6, 9. So what we've just done is we've taken this original parent parabola and we've made it wider by a factor of 2. So there is your horizontal stretch. And now our last example, let's do a shrink. So I think I have room down here. So our last example, let's do a horizontal shrink of the absolute value function by a half its size. So instead of twice its size, it's going to be half of its size. So h of x is equal to, we've got the absolute value function, and if it's half the size, you're going to have to put a 2x, because we're dividing the x's by 2 if you want it half the size. Divide x's by 2. So let's set up our xy table for absolute value, -3, -2, -1, 0, 1, 2, and 3, and absolute value. So now if we're dividing x's by 2, we'll just say a half x as our new xy table. So -3 halves, or -3 over 2 is -1.5. -2 over 2 is -1. -1 over 2 is -0.5. 0 over 2 is still 0. 0.5, 1, and 1.5. So those x's have gone in half and the y's stay the same. Oops, 3, 2, 1, 0, 1, 2, 3. So let's take those values and plot them on our graph. Looks like the y's are going to be all positive. So we have to go back to -2 on our x and to +2, and we're going up to 3. 1, 2, 3. So -1.5 is about right here. 3. -1, 2. -1/2, 1. 0, 0. Oops, I didn't go high enough on that. Sorry about that. 1/2, 1. 1, 2. And 1.5, 3. Which is about up to there. So now we can just connect this because this is absolute value. We've got a V-shaped graph. Here on the other side. Oops, that's not too symmetric. This should be symmetric across the y-axis. But you can see that this has been horizontally shrunk. Usually an absolute value graph is a wider one, but we've just shrunk this down to half of its size. And that's all I have tonight. So I hope you have a good day, and I'll see you tomorrow.